Dr. Palmisano, and I'm going to be talking to you today about big data architecture. In this presentation, I'll be talking about the various storage options that you have when building your big data architecture, as well as your different platform options you have, your network options, specifically an any-to-any topology versus a switching fabric network, and I will also be talking about the data, which is the most important part of big data, and its collection, presentation, and visualization. So first, let's get into storage. One reason that big data is called big data is because of the large data sets used with it. In the past, organizations haven't really had to worry about data storage, but with how large these sets of data are, it's something that they need to consider when building this architecture up. One option that a lot of organizations and companies are going with is relational databases. These have been around since the late 60s, early 70s, which means that a lot of people who are working in these companies have experience with them in some manner or another. So they are familiar with them, they are comfortable working with them, and that means they're most efficient working in this format. The downside to these options, though, is that they are rather expensive. It's found through one study that storing 1 terabyte of data on a relational database for 1 year cost an organization roughly $37,000. Because of the prevalence of big data, Apache has decided that they wanted to find a better way, or better in their eyes at least, to manage these data sets, and they created Hadoop, which is a big data framework that has become very popular and has lots of spin-offs and alternatives now. It stores data in clusters as opposed to just all in one place. It breaks the data up into chunks and distributes it throughout a distributed file system instead. This makes processing the data much more efficient because it's running everything on a smaller subset. And it's also been found through the same study that tested the cost of a relational database that it is massively cheaper. It only costs about $2,000 as opposed to that $37,000 to store the same terabyte of data for a year. The image at the right here shows a good, if fairly simplistic, depiction of the Hadoop distributed file system design. The client at the top can communicate with the name node on the left, which can communicate with both the job tracker and multiple servers looking for data stored across all of them. This is where you see the chunked up data stored in different clusters. The name node and the client can both talk to the tracker, which is looking at the servers for tasks instead of data, which are also broken up and stored in a distributed fashion. Next up is the options that an organization can consider when talking about the different platforms that it can utilize big data on. Typically, when referring to a platform for big data, people are talking about the features and functionalities offered by one solution that can help to develop, deploy, operate, and manage these large sets of data. There's dozens of different platforms available for organizations to choose from nowadays, and some of those may work better than others for an organization's specific needs. One of the options that many organizations go for is some sort of use with SQL. And a lot of that is through a traditional database, a relational database, or SQL on Hadoop. And people go with this option because, again, it's familiar. It's been around since the late 60s, early 70s. And it's really, really good at pulling out structured data from large data sets. But that's about the extent of the maximum utility for SQL. For most big data platforms, your best option to maximize your use of it is going for something more like machine learning, which is your software and stuff learning without being explicitly told what it's doing, and time series analysis, which is kind of exactly like it sounds, analyzing data over a time period. Other things that organizations need to consider when looking at a platform is data ingestion and management and stream computing. Data ingestion is also aptly named as it refers to obtaining and importing data into an organization and either preparing it for use immediately or sending it to storage. This can be done either in real time or in batches. The data management part of that refers more to the aspects of the access to the data, the quality of the data, integration of the data into the system, and other things like that. Stream computing is more of a way to supplement and enhance a big data architecture than it is something to stand on its own. Its primary function is powering low latency velocities without relying on the high volume storage that a lot of this stuff needs. It's really good at picking up the slack where something is running a little slower than you would like it to, and having that extra data being processed helps speed up your system and makes that data more ready for use. Next up are the different networking designs that organizations can consider when building their big data architecture. I'll just be talking about two primarily. Like I said earlier, one of the most popular solutions that organizations who want to use big data choose to use is Hadoop or some other form of a Hadoop-based system. Hadoop tends to work best with an any-to-any network architecture, and that any-to-any term is generally referring to the use of multi-protocol label switching to speed up the network traffic and also make it easier to manage. That increased speed is incredibly useful to the network, especially when it comes to getting that data into a Hadoop cluster. If your network isn't set up in this way, getting that data in is often one of the very first bottlenecks reached in the system, and that can really hamper the productivity of your big data usage. Another thing that Hadoop requires, which is satisfied by an any-to-any network architecture, is high availability and fault tolerance. Hadoop needs something that won't really ever go down and is generally really accessible. A network like any-to-any is exactly that. If one node in the network goes down, every single other node is still accessible through at least one other node, but actually through all of them, because it's an any-to-any, it's in the name. Another architecture that a lot of organizations use, this one isn't for Hadoop, this one is actually recommended by IBM for theirs, is a scalable switching fabric network architecture. And it's in the name that it is scalable just like an any-to-any network architecture is. And it is actually also an incredibly fast architecture. One of the biggest differences between the switching fabric network architecture and the any-to-any network architecture is how the nodes in the network are connected. The any-to-any network architecture has direct links from every node to every other node, whereas switching fabric network architecture has direct links from nodes to switches only, and the switches are what links these nodes to the other nodes. They work together to create the point-to-point connection mechanism amongst the nodes and reduce the latency between them. With this type of network architecture, it's recommended that the switching fabric is a virtual switching fabric, and doing that allows you to have multiple components working together within the network to behave as one component, which is much more efficient than numerous components all acting independently of each other. The pictures on the right show great examples of both types of network architectures. In the bottom right, you have your any-to-any network architecture, where every node is directly linked to another node via one of the blue lines there. In the top left architecture, you have an example of a Facebook data center fabric network actually. You can see each of those dots represents a switch, and this is noticeable because you can see a line going to every single node, which are in the yellow boxes. Last but not least is the data and how it's collected and how it's presented. Arguably, the most important part of a big data architecture is the data itself. And this shouldn't come as much of a surprise because you could have the best storage system out there, you could be using the best big data platform available, and you could have the best network with the highest reliability and the fastest speeds, and none of that would matter if you didn't have any data to use it on, or you couldn't present that data in a useful manner. Different organizations are going to require different types of data depending on what they do, and so the way they collect their data may vary. Common ways that organizations collect data are sensors. Some common sensors would be like a GPS, a gyroscope, an accelerometer, things in devices like that. Different apps collect user data and send it back to an organization. Video camera footage from something like a security camera or a closed circuit television. Beacons of kinds. Customer information request is a huge one. On websites where users fill out forms, all of that data is typically stored and used in some fashion. Social media is another one where an organization may crawl across social media and collect data that way. Some of the most common types of data that are collected would be percent of visitors to a web page, percentage of visitors who view a product page, percent of the people who search for the site or search on the site and then immediately exit, page load speeds, average order values on a site that sells things, completion of tasks by a user on a website, and conversion rates of users. And all of that data, while being collected is great, still doesn't mean anything if it can't be visualized or presented to the decision makers in a useful format. Some of the most conventional methods that people use would be things like a bar graph, line graph, scatter plot, pie chart, histogram, those types of things. And those are really great for a lot of the more basic data analysis tools, maybe like revenue over time or inventory, things like that. But with all the new methods of data analysis out there, with more complex analysis, organizations are looking for easier ways to visualize things that might not necessarily be as clear with those conventional methods. There are different softwares and things like that out there, that like Tableau, HighCharts, as two examples, that are extremely user-friendly and more accessible typically because they have some sort of online portal or they're an online workspace, and they can be incredibly useful and create new and unique types of ways that people can present their data and visualize what's going on through all of this analysis. With big data becoming one of the more popular avenues for organizations to try to get a leg up on their competition nowadays, it's important for those organizations to consider the architecture that they're performing all of this data analysis on. They need to consider the storage options, whether they want to use a relational database or something like a Hadoop distributed file system. They need to consider which type of platform they want to use, whether that's something really basic and SQL oriented or something more complex like machine learning or time series analysis. They need to consider the network setup that they have, whether that be something like an any-to-any network or a switching fabric network. It just depends on which platform you're using as to what network is most suitable for you. And most importantly, they need to consider how they're going to be collecting their data and how they're going to present that to the people who need to see it the most. If an organization carefully considers all of its options for these categories and they make the right choices, this can tremendously benefit that organization. So that's what I've got for you on big data architectures. If you have any questions, feel free to ask them in the discussion board. I'll do my best to answer them. Thanks for watching.